All right, so what we've been doing up to this point in the course, we have been focusing on particle kinematics. And so I figured I'd bring this up so that we remember where we're at in the big picture of the whole course. Where we are at, basically where we have been, has been this, little block down here. And one of the things that I said early on was that we build all the other stuff that we do in dynamics on the foundation of kinematics, right? How things move, like actually describing how things move is the kinematic side. Describing why they move or how we can predict how something might move is more of a kinetics kind of a endeavor. And so we are transitioning today, where we've been doing kinematics, we're transitioning into doing more a kinetics kind of study. And the particular block that we're going to look at is this block right here, where we use Newton's second law in order to look at things like basically the influences that change how something moves. And so we're going to look at F equals ma today, and we're going to then relate forces to how things move. So we're going to try to get to the rest of this little figure here also throughout the course, but here's where we're at right now. We're going to add this little block, that little pink block right there. All right, so by way of description of this, let me go ahead and show an example of how this works, at least in general terms. Let's say that we have a ball that is rolling in a parabolic track and it has a rope attached to it, tied to it. We can represent a scenario like this with, really with Newton's second law. We can sum forces. Okay, those are vector quantities, and set them equal to mass times acceleration, where acceleration is also a vector quantity. Each of these sort of phases of the problem have their own diagram that go along with it. We are already very comfortable, or should be very comfortable, with the idea of drawing a diagram related to a sum of forces, right? This is the same kind of diagram that we do when we study statics. So if you look at that ball, in conceptual terms, we could kind of describe all the forces acting on that ball. We could say that there's a force coming from the rope. Okay, there's a force from the rope. Okay, what other forces happen on the ball? Well, let's say it's in gravity, right? So it might have some weight pulling down on it like this. Other forces that you might have acting on here would probably be best aligned with sort of the tangential direction of this track, all right? Kind of our normal tangential idea of how coordinates can be set up. And you could either have, or you can have both, or any combination of an acceleration or velocities that are tangential to the track, right? Or you can have forces that would be tangential to that track. If it's a smooth track, right, then there's not necessarily a reason why there would be. If this track has friction in it, you definitely would expect that you would have a component of force that would be acting there. So let's say that you're trying to wind this, particle up the track. Well, then what you'd expect would happen there would be that there would be some friction force that would resist that, right, if you're trying to wind it up there. The other thing that you could have happen here is that the track could actually put a force on the particle in a normal direction, right? So a normal force here. Okay, so these are all forces that might act on that little body that basically is like a particle. We would generally kind of define some sort of a coordinate system in which we were working. We could call it x, y. Or, just a second ago I got finished saying that we had another coordinate system you might consider using here, one where it would be a tangential and normal type of a coordinate system. All right. So anyway, that is what the sum of forces diagram, that's what you use to do that part of the problem, is to use a free body diagram, that's what this is called, to assist you in the process of coming up with all the forces that act on a body. Okay? The other half is actually something that is called a kinetic diagram. All right? And that's where you start looking at what does this little particle or ball or whatever body it is that you're looking at, what does it do in response? Okay? And I would say that, let's say the ball starts moving up the track, one thing that we could expect, one type of acceleration, for instance, that we could expect would be one that would be pointed in toward the middle of this curved track, right? What kind of acceleration is that? We gave that a name. We would generally call that a centripetal acceleration, right? But anyway, that is a normal component of acceleration. Okay, and then the other thing that we could have is we could have an acceleration that would be directed, you know, in the direction of the track. So this would be a tangential acceleration. And the normal and tangential components of acceleration would be things that if you knew how the part was moving, you would have math that you could do that could tell you the magnitudes of each of those values. At least that's what we've been working on, right? That's the type of work that we've been doing. Okay, we can also set up some coordinate systems on here. It's not uncommon for you to try to use the same coordinate systems as what you did for the free body diagram. Okay, and you could have multiple coordinate systems if that was something that was helpful. Anyway, this whole idea over here is that you can set up a kinetic diagram. Because there are fewer, I guess there's a wider variety of different types of ways that you can be given how a body might be moving, right? That universe is fairly large. It's harder to establish specific rules for establishing a kinetic diagram like there is for a free body diagram, okay? But it's nice to have another diagram where you can indicate on there, here are all the ways that it might be moving. You can put velocities, you can put accelerations, you can even make some sort of an indication of how far something has moved, for instance. That's more of a geometry diagram, but anyway, the idea is don't be afraid to make diagrams that describe this geometrical stuff that would be important for the kinetic diagram, okay? And ultimately what you're trying to do is make the process easier for you to sum forces and relate it to the mass times the acceleration ultimately that the CG of the body experiences. That's kind of an important thing that's going to start mattering more when we go into rigid body dynamics instead of particle dynamics. Once you go to rigid body dynamics, it's important to understand that the accelerations that we're talking about need to be the center of mass, and then we'll do other stuff that deals with the rotational or the potential for rotational motion for those bodies. Okay, but for now, just understand that particles, kind of by their very nature, we kind of expect that all the forces are going to go through the center of mass. All right? So let's do an example. Here you have a particle that begins in a slot. All right? The slot is open on one end, and I mentioned here that it's in space. The reason I say that is that I don't want you to think that you have to apply any sort of gravitational, additional gravitational acceleration to this body. This is out there sort of free, not experiencing a gravitational pull. The influence on that particle is given with the vector expression that I'm showing right there. So that's actually an acceleration as a function of time. Okay, both in the x and the y direction given with the I and j components there. All right, so in the first part of the motion of the particle, it is guided by a frictionless slot, and then once it exits the slot, then it's sort of on its own and it will move however the forces that are applied to it there would influence it. So what we're supposed to find here is first the time at which the particle exits the slot and the components of velocity at that time. So that's the first thing we want to do. Once we get that, the next half of the problem is to find the position of the particle after a total of 2 seconds elapses. That includes the amount of time that it took for it to be launched out of the slot, right? So we need to kind of start a second part of the problem. We're not starting at time 0 at that point. We're including the time that the particle was accelerated at the very beginning. All right? So here's what I want to do first. We are given an expression here that already gives us force as a function of time. All right? So what's interesting about this problem is that if I'm going to do a little free body diagram, it's probably a good idea to do one, but it's not actually all that interesting because here, I guess for the first part of the problem, you have a component of force that is given here in the x direction, right? And I'll just call this the x component of force as a function of t, right? And you're also given a y component of force given as a function of t. Okay, that's not super interesting just yet, all right? But what else? What other things happen when you're in the first phase of this problem while you're still in the slot? What other kind of force can be applied to the particle while it's in the slot if it's frictionless? Okay, if it's frictionless, the only other component of force that you can have would be some sort of a normal component to the slot. So if you kind of imagine there being another force like this, I'll call that maybe F sub n. It's not just a constant value, it is also going to be a function of t, most likely. Okay, and it's going to only have that component that is applied from the slot because it is frictionless. Okay, all right. This now is going to lead us to our kinetic diagram. What's the kinetic diagram look like? Okay, we don't want to overthink this. The kinetic diagram, at least when we're in the first phase of the problem while we're in the slot, can the particle move any direction besides the direction of the slot? No, that's the point of the slot is to constrain it to move only along that line. And therefore, the entire acceleration that we have of this body, of this particle, is going to be along that line. All right? Because it's being constrained that way. And so if you want to set this up relative to some axes like this, probably should go back and put axes on my other one over here as well. Okay. One thing we know here is that we have a 25-degree elevation of this acceleration. And I'm actually going to call this A sub t, where the sub t represents tangential, right? It's in a slot. The direction it's moving is the direction of the path. That's the tangential component. And it is also going to be a function of t. Okay? And that's the only component of acceleration that I have at this point. All right. Why do I set this up? Well, in addition to it being just a good idea to do free body diagram and kinetic diagram for just about every problem that you do, that at least a problem like this where you're using Newton's second law, the other reason that I do this is to illustrate the point that if I sort of scrap my x and y components or x and y coordinate system and go to my normal tangential coordinate system, then what I can do is basically eliminate my normal component of force from the resulting equation. One reason I might want to do that is that I don't know what that thing is just yet. That's it's being applied. I know there's a force being applied, but I don't know a function or anything that gives that to me. So what I'm going to do is go and because I would like to use normal and tangential coordinates here, and really it's the tangential one I care most about, I can take my Fy and Fx and convert them into a force along the tangential direction. Okay, well, how do I do that? Here's how I think about doing that. I'm going to draw a line here that would be in my tangential direction, right? And I can see there that there is a component of Fx that projects onto that line. Do you agree with that? All right. And what is this angle right here? That angle right there should be 25 degrees, right? And so the component that I have then that projects onto this tangential axis right here is going to be, I'm going to start writing this tangential force here. I'm going to have whatever Fx was as a function of t multiplied by the cosine of 25 degrees. Okay? That's the contribution of the x force that I have being applied. Okay? Is that all of what I need? I would say no, because I also have Fy. If I look at Fy, it contributes another amount if you project it onto that tangential axis, right? So these two amounts that I have there would add together and make the overall amount of force that's being applied in the tangential direction due to the this force that's applied somehow, and I've given you the functions for how it's, exactly how that progresses over time. All right. So what we want to do next with that is we want to actually establish that there is an acceleration that happens due to these forces that are being applied. All right. So to do that, basically I go through and I divide by my mass. All right. How much mass do I have? Well, I have 5 pounds mass. Okay. This is actually something that I should probably deal with right now. I'm showing it up here because I want to do at least one example where pounds mass shows up. I hate pounds mass. Okay, this is an abomination that pounds mass exists, right? But it does, and it exists other places besides in your textbook. It exists, in reference materials that you might have to look at in your career, and it's all over the place. So we have to deal with it. What I think the best way is to deal with pounds mass is to, as quickly as possible, express it in terms of slugs. All right, slug is a proper unit of mass when you're dealing with these kinds of problems, and the conversion factor to go from pounds mass to slugs is 32.2. There are 32.2 pounds mass in a slug. Okay, so what we do there, I'll kind of do this over here to the side, 5 pounds mass times, okay, there are 32.2 pounds mass in a slug. All right, this tells me here that my amount of mass for this body is just going to be equal to 5 divided by 32.2. Okay, or 1.553, we'll say, or 0.1553. And that would be in units of slugs. Okay, that is going to be something I use a lot. Let me go ahead and store that into variable, or in my constant A that I have there in my calculator. And to remember that, I'm going to go over here and say this is stored in A. All right, Well, let me actually start putting these in here then and writing this stuff out. So if I divide this by m, okay, what this gives me is an acceleration in a tangential direction. Would you agree with that? And I would have to divide all of this stuff by the mass. All right, this is because F equals ma. Another way to say that is that A is equal to F over m. Okay? And so what I'm going to do here is go from this expression to a velocity along the tangential direction. Basically what I'd like to do here ultimately is integrate this expression for acceleration twice so that I can get position, because one of the things I know is that this thing moves 2 feet before it goes out of the slot right there. So if I can go from acceleration to displacement, then that lets me relate to that 2 feet of travel that I have up there along the tangential direction. Okay, so v of t, this is actually v sub t for the tangential direction as a function of t time. This is going to be equal to, what you'll notice there is that cosine of 25 degrees as well as m are both constants. So I am going to pull those out like this, where I have cosine of 25 degrees, okay, divided by my mass, and the mass is just 0.1553 slugs. Okay. I need to integrate now from 0 to what? Okay, well, that's actually what I'm supposed to find. The time when the particle exits the slot. That's the variable I'm looking for. Okay, so from 0 to t, so I'll just leave that in terms of a variable there. And what I need to do now is, for this first expression, I'm only going to use the x component expression up there. Okay? The other thing that I'm going to show here is that pounds force is multiplied through that whole expression, right? So it's kind of like a constant as well. So I'm going to pull that out as well. I'm going to take this out here and say I've got pounds force outside of this integral. All right? Leaving inside the integral, I will have minus 0.3. This will be per second. All right, so I could actually maybe write that like this. Minus 0.3 per second squared. All right? T squared plus, all right, 4 per second t plus 2, all right, that won't have t or s in it, or seconds, all right, and then all of this is going to be dt. That is the contribution to my tangential velocity from the x component of force. To this, I need to add the contribution from my y component of force, and that is just going to be equal to the sine of 25 degrees. Okay. Again, I'll pull out my pounds force. Down here I have the mass. Okay. And this is all going to get multiplied by the integral from 0 to t, and now I need to put in the expression that I had up here for the y. So that'll be minus 1 over seconds t plus 1. All right, dt. All right, so there is an expression that I have for the velocity. What I need to do now is actually integrate it. All right. Real quick, another sidebar that I'll do over here before I integrate that. What is a pound force per slug? So pound force per slug is equal to, the definition of a pound force is a slug foot per second squared. All right? So this is going to be equal to slug foot per second squared per slug. All right? Which means that the slugs just cancel out, and what am I left with? If I have pound force per slug, I'm just left with foot per second squared. Okay? So one of the things, I'll do a couple things here. First of all, cosine of 25 degrees is just a constant. And so I'm going to go in here and combine that constant with the slug that I have, the number of slugs I have in the denominator, and I end up with just cosine of 25 divided by what I had stored in A, like this. And what that gives me is a constant that I can put out in front of the first integral there, and I can express that in terms of foot per second squared. So 5.8366. Let me do this real quick as well. I'm going to store that into variable b. Okay, 5.836. Okay, and this is in foot per second squared, and I'm going to go ahead and kind of make a note there that that is in variable or constant b that I have in the calculator. All right. So this gets multiplied by, let me go ahead and do this integral real quick. I increase the exponent by 1, divide by the new exponent. That gives me minus 0.1 over second squared t cubed, plus here I have 2 over second t squared, plus here I have 2t. All right. The next piece that I should do is probably my other constant that I have in front there. So that will be sine of 25 degrees divided by, again, what I have in A is the mass in slugs. So that gives me 2.722 foot per second squared. Let me store that in my variable c. All right. Now let me do this integral. Okay. Increase the exponent of t by 1, divide by the new exponent. So that basically gives me minus 1 over 2 seconds t squared plus, and here I have just t. All right. So there is my expression for velocity in terms of t. What do you think the next step is? All right. We're trying to get to position, right, or displacement. This book sometimes uses the letter S to describe displacement, so that's what I will do here. This is displacement along the tangential direction as a function of t, right? Rather than write all this out, let me just say I'm integrating here. Okay? And when I integrate, what I end up with is I will still have the same constant out in front, 5.837 foot per second squared. Okay. What I end up with here is, again, I increase the exponent by 1, divide by the new exponent. Okay. Like this. Okay. The next term, increase it by 1, divide by the new exponent. That would give me 2 over 3 seconds t cubed. And the next one I would have, that goes to t squared. And so I end up with 2 over 2 gives me just t squared without anything else in front of it. Okay, that's for one term. Okay, the next term is still going to have that same constant of 2.722 foot per second squared out in front. And here I need to increase that exponent by 1, divide by the new exponent. That basically gives me here minus 1 over 6s, 6 seconds that should be, t cubed, plus increase that exponent by 1 gives you t squared, and divide by the new exponent gives you 1/2. All right. Why did all this matter? Well, we had to do all of that because I actually want to find t, right? That's what I'm trying to find is t when s as a function of t, s sub t as a function of t is equal to what? 2 feet, right? Because I'm basically integrating to find the amount of time it takes to progress 2 feet of displacement, right? So what I'm basically saying here is that s sub t, the tangential component of displacement, at some time t, all right, and actually I can, if I want, I can just put a little subscript on here, maybe t sub e, for the time at exit, right? That's the time at, amount of time that's elapsed at the point that it exits. This is going to be equal to 2 feet. Okay, and I can basically solve that expression in the Casio. Okay, so solve in the Casio. Here's how that looks. Okay, we plug in 2 feet first. So here we've got 2 is equal to, all right, I had 5.837 stored in variable b. Okay, I'm going to take that and multiply it by, here I'm going to put minus a fraction of 0.1 over 4. The variable that I'm going to use is x, and that's going to be to the 4th power, plus, here I have another fraction, 2 times x, go ahead and put that up there, to the 3rd power over 3. Next I have another t squared. All right. To this I'm going to add what I have stored in variable c. That is that 2.722 foot per second squared, multiplied by, all right, here I've got negative x cubed over 6 plus x squared over 2. Okay, and remember this is an equation that I'm writing right here, right? And I'm trying to find x. So I'm going to say shift solve. It's going to ask, is this what you want in B? Yep, that's what I want in B. Is this what you want in C? Yes, that's what I want in C. Here's your initial value for x for its iterative technique that it uses internally. I don't have a reason to doubt something in that order of magnitude or so. And so I'm going to hit equals again, and it will solve and tell me that it is 0.477 seconds t sub e. Okay. And I tell you what, I'm going to take that value here. To do that, I'll it's actually still got that value stored in x, right? If I want to take that value and store it into another variable, because I use x for a lot of things, I'm going to do that real quick. I'm going to store it. I'm just going to use f. Okay? So I've got that time value stored in f. Okay, so that was actually one of the things that we were supposed to try to find, right? The amount of time that it took for the particle to exit the slot. All right, what was another thing we were supposed to find? Time when the particle exits the slot and the velocity at that time. And I want to do that in terms of two components of velocity. All right, so how do I go there? Okay, right. Okay, keep in mind this is B, this is C. I have an expression for V sub t of t, right? The tangential component of velocity at time t. And so I can just plug that value that I have now for t sub e back into this expression up here, and it will give me my velocity at exit. Okay, so we'll do that. What I have there is, B times, all right, here I've got negative 0.1 times t, okay, I'm going to plug in f there. I need to actually explicitly multiply that, cubed, plus, okay, here I've got 2 times f squared. Next, I've got 2 times f. Okay, and to this I'm going to add the value I have stored in C times. Here I've got minus, all right, f, that should be squared, over 2 plus f. All right. And when it crunches all of that, it ends up giving me a tangential velocity at exit of 9.141. So 9.141 foot per second. Okay. So let me store that temporarily here. I'm just going to store that in m real quick. Ultimately, what I want is not so much that total velocity, because the next part of the problem, I need that velocity split up into components, x and y components, for the next phase of this same problem. So to get that split up into components, we just use the fact that we know the angle that it launches at, right? So if I want to get an x component, for instance, I can take this value of 9.141 and multiply it by the cosine of 25 degrees. Okay, so I better write that out so that it's not confusing what I'm doing there. So we'll say the velocity in the x direction at exit, all right, is going to be equal to the velocity in the tangential direction at that exit time times the cosine of 25 degrees. That's what I just did. And so what that gives me is 8.285. And that's in foot per second. Okay. What do you think you do for the y component? We basically do the same thing, but multiply by the sine of 25 degrees instead of the cosine. Okay. Before I leave here, this is actually a result that I'm probably going to need, here or there. And so let me go ahead and get that stored into, I'll go ahead and get it stored. I believe I've used A, B, and C so far. Let me use D. Okay, and I'll put that right here. All right, the next one is, I'm going to take what I had temporarily stored in M times the sine of 25 degrees. Okay, that gives me 3.863. Foot per second. All right, and let me store that one into E. All right, so now we have completely finished part A of the problem. We know the exit velocity, and we know how much time it took for that exit velocity to be achieved. All right, so what's next? Should go back and remember. The position of the particle after a total of 2 seconds elapses. All right? There's a couple reasons why this is tricky. All right? One of the reasons is that the behavior of the particle is now different. Right? The behavior of the particle, it's now free. The first part of this problem was a constrained motion problem because it was constrained by the slot. The second part of the problem is a free motion problem. It means that we look at the amount of force being applied, and that is what's going to control where the particle ultimately goes. Okay? Other than that, it actually looks kind of similar, but I guess we should probably go and, for part B, look at maybe a different kind of free body diagram, because now we no longer have the slot that's involved. Yeah?
Since there's no friction and we're in space,
Mm-hmm.
or do you continue along the path previously established by the force?
Ask that one more time. You said it. Go ahead.
So since we're in space,
Yeah.
since there's no friction,
Uh-huh.
it's not going to be acted upon by another force, so therefore shouldn't it just continue on the path of barreling?
Okay, good question. So it sounds like you're basically interpreting this as like a gun that's shooting this out, and that's not bad instinct as long as this force doesn't continue. This is basically a force vector over time. This is going to continually be applied to the particle even after it leaves the barrel of the gun, as it's easy to picture this, right? So if that's the case, then if this force is still an influence that's happening, it's not going to continue in a straight line because this is going to have an influence moving it away from being just a simple straight line. Okay, good thought. All right, so let's do this. Let's first of all come up with our like a position function here. To do that, we have to start with acceleration. Actually, back up a second. I was about to do a free body diagram kind of a thing, so let me do that. All right, we have, again, not very interesting free body diagram here because we have still just the x component of force as a function of time and a y component of force as a function of time. Now we don't even have the interesting part of having a normal force coming from the slot that it was riding in. So that kind of goes away. And so because all of that happens and because now we're no longer constrained, the best we can do is we can basically just say that this is going to be equal to that same particle experiencing two different components of acceleration like this. But the nice thing about this is that I can basically just relate my forces in the x direction with my acceleration in the x direction. I can relate my force in the y direction with my acceleration in the y direction. Okay? So again, that's not very interesting, but it's a good idea to probably put what you know down on your free body diagram as well as on your kinetic diagram. All right, so let's start in the x direction. So my acceleration as a function of t, all right, is again going to be equal to the force in the x direction as a function of t divided by the mass. Okay, and so this ends up just giving me pounds force per, the mass was 0.1553 slugs. Okay. This is going to be multiplied by the expression that I have for force, right, which was way up here, negative 0.3 t squared plus 4 t plus 2. Okay. And keep in mind that well, pounds force over slugs gives me what kind of units? Right, feet per second squared. So what this ends up giving me here, if I integrate, okay, what it ends up giving me is an x velocity as a function of t, which is going to be equal to 1 over 0.1553 slugs. Whoop, the slug goes away, right? All right, and this would be in units of foot per second squared. Okay, now here's our first tricky thing. Okay, when I integrate to get this velocity, we are used to normally starting at a time of 0. All right, do I want to do that on this problem? Okay, keep in mind, this is the phase of the problem after it leaves the slot. Okay, and because it's leaving the slot, we don't actually want to integrate from time 0, because one of the things we said at the very beginning was we want 2 seconds total elapsed time, right? Which means that this function that we're trying to integrate right here, the time that exists for this function is that time at exit, right? So our beginning time right here is going to be this 0.477 seconds. Okay, and then ultimately we're supposed to go to a completion time of what? 2 seconds. Okay, so we put that at the upper limit. Okay, and when we integrate this, it's going to look very similar to what we did last time, right? It's going to be negative 0.1 over second squared t cubed plus 2 over seconds t squared plus 2t, right? Now here's the other thing that's tricky. When I integrate this, there's another component that I need in here, and it's something you often have to do when you integrate, right? If you have initial conditions. And that's another thing that I have in this problem, is that I do have an initial condition of that initial x exit velocity, right? 8.285 feet per second. All right, and that's outside of this integral, right? So this is, that's the end of my integral right there, dt. All right. Well, since we don't have a zero lower limit, that makes this just a little bit more painful. Okay, and what it basically means is that I have to I shouldn't have, hang on, let me fix this right here. I did this integration too soon. All right, this is what I wanted in here. I was about to integrate that right there. Got a little bit too eager. Right? Okay. So, this is what I get when I integrate that, but then I have to subtract the case where I have, and this, let me do this right here as well. I'm going to do this up to time t so that it's general enough that I can take another derivative, right? Because that's ultimately something that I'm going to need to do. So a couple of things I got a little bit eager on there. Okay, so I put in t here, and then I go basically this again, but I plug in whatever that time is at exit. All right. Okay, so the t's that I have here, I'm going to put a little sub e on each one of them. And keep in mind that t sub e was equal to 0.477 seconds. All right, and I then don't want to forget that I have added 8.285 foot per second. Okay, so this is just as a matter of interest. T sub e is equal to 0.477 seconds. All right, now, one of the things to note here is that all of this stuff over here is a constant, right? All of that is just constant, okay? And if I plug those values in, I tell you what, that's not very interesting, and it'll take a while. I will skip ahead just a little bit here. One of the things you get with this is, let's see, I'm going to copy this in here one more time. Okay. And you can combine these together, and what it ends up giving you is a negative 0.7112 feet per second. The reason I do that is just to make it simpler for the next step, which is integrating again. Yes, sir.
Just real quick, for part B, we're trying to figure out 2 seconds after it exits the
Right, so 2 seconds, sorry, total elapsed time.
Why can't we just plug that 0 to 2 seconds in the first displacement?
The reason why is that you have guided motion at the beginning. So the slot messes with it, right? You can't just plug this in all the way from the beginning because the slot is guiding the motion at the beginning of the problem. You know the exact position where it leaves, and you know the components of velocity you have at that time. And this will actually, you know, what you actually see there, this difference that you're seeing right there, one way to interpret that is the difference that you have between the case that you're describing. You're thinking, well, why couldn't we just integrate it all the way from the beginning? That 0.7112 feet per second is the difference between those two ideas, right? And it's happening because that slot is guiding the motion in that first phase of the problem. All right, so what we need to do next is we need to get the position, right? And I tell you what, we don't have to go anywhere past this position in the x direction. And if you're doing you know, these problems with the Casio calculator, the Casio has the ability to evaluate integrals at particular points in time. And so there's no reason I need a formulaic setup of the you know, of this function. What I can do is basically just integrate this. I'll show you this here in just a second. Before I do that, I'll write it down. I need to basically take the integral from 0.477 seconds up to, okay, where I put t sub f right here, I'm using that as a variable to describe that 2 seconds, right? That's like the final time that I'm trying to evaluate it at. So 2 seconds in for t sub f. Okay, and I put in this same exact function. Okay. Okay. And ultimately, I put this in the wrong place. I want this integration to happen for the whole, right, for all of this stuff. So including the minus 0.7112 feet per second. So the integral would actually happen way out here, like this, and it would again be from 0.477 seconds up to 2 seconds, or t sub f. If you had a different final time, you would just put it in there. So we're going to use 2 seconds for our givens in this problem. All right, and this actually is kind of interesting. In case you haven't done this before in the calculator, I do want to show you this. So, and I think I have all these variables that make it really nice to put it in here. Basically, what I'm going to do is do an integral of 1 over, okay, I think I have that stored in A, the mass there. All right, that gets multiplied by here I have negative 0.1 x cubed plus 2 x squared plus 2 x, oops, all right, make sure I've got my parentheses right here, all right. And then I'm going to subtract 0.7112. Okay. I need to integrate this from, I believe I had that initial time, or that exit time, 0.477 seconds. I believe I had that stored in F, and I'm going up to 2. All right. And if I did all that right, it should give me 54.53. Units? Feet. Okay, so that's half of the position question that we had just a second ago. What do you think you do for the y direction? Is it any different? Okay, I'll go through this one as quick as I can because it's not really different than the x direction that we just did. So again, we start with the acceleration function, which is just the force function over the mass, okay, which is just equal to pounds force over 0.1553 slug, okay, multiplied by minus 1 over s times t plus 1. Okay. To go to velocity, okay, keep in mind the pounds force over slug is just foot per second squared, so I go to 1 over 0.1553 foot per second squared. This will be multiplied by the integral from 0.477 seconds up to, again, I'll just express this generally in terms of t. All right, of this minus 1 over seconds times t plus 1 dt plus that initial velocity in that direction, which was 3.863 feet per second. All right, and what does that give me? Okay, what that gives me is 1 over 1.1553 feet per second squared times, okay, here I would end up with minus 1 over 2 seconds t squared plus t minus a minus 1 over 2 seconds. This is our exit time squared plus our exit time plus that initial velocity. All right, so then we move on and collect our constant terms. Okay, meaning that I just have the ones that have t's in them here, and I'm going to collect, you know, all of this stuff into one term. That term becomes 1.525 feet per second. Okay. And now I can take that and integrate it to get my position in the y. Okay. By the way, one of the reasons I could do this, I didn't have a constant that I added into the position in the x. What was the reason for that? Okay, if you go back to the beginning, this phase of the flight, right, begins where? At the origin, like where I have established the origin, right? So that's why I don't need initial positions in either the x or the y. I didn't really mention that before, so I went back and mentioned that. All right, so what do I do here? Well, it's kind of the same thing I did last time, right? I need to take the integral of 1 over what I have stored in A times, okay, in the parentheses here, I'll put negative x squared over 2 plus x plus 1.525. Okay, this is going to be integrated from 0.4. I'm going to do it this way. I think I have that in f going up to 2 seconds. Okay, and that gives me 6.001. And that would be in feet. All right. Questions on that one? Yes, sir.
We wanted to know position after 2 seconds.
Yes.
Do you have to add the 54 to the original position since that's only 0.477 seconds to 2 seconds, and that's not a full integration over 2 seconds?
So what happened in the first half second, right, or a little bit less than half second, was the particle progressed from being at the back of the slot to the edge of the slot, right? So that's what happened in the first half second of this 2 seconds, right? What we're curious about from that point on is what happens out here in the freedom, right? And so, we have to integrate so that we are plugging the proper values in for t in for this expression, because what we're assuming here is that time begins back here. That's time 0, right? Shown at time 0, right? So time begins back there, and so we do begin with sort of a negative x and negative y initial position, so to speak, and then it progresses up to where x and y position are 0 at time equal 0.477 seconds, right? And then we progress on from there to what happens out in the free space under the influence of this force.
So whenever it says total time of 2 seconds, that means like total time that it started at the...
Yep.
So you're not changing the time, but you're changing the origin of the particle as it goes through.
I guess so, yeah. I'm not claiming to start the particle at the origin at time 0, right? I'm basically placing the origin at the exit of the launch slot, whatever that is. Okay? Other questions?